which I didn't really like.
Okay, now it looks like it's full screen.
And it's not progressing. Okay, let's get started. Do you want to say anything to the group, Anita, or should I just get going? Probably they all know what's going on by now.
Yeah, this is the last lecture. That's what I can say. That's the last lecture of the series of 3. And we are really happy to have Professor David Van Dyke giving that lecture. So I hope people enjoyed. And today is the last day of David's visit, but I'm sure he will be back.
I am. My luggage is in my office.
Okay.
To go. Not till 10 p.m. though, so there's plenty of time.
Okay.
Anyway, so if you remember the first lecture, we talked about basics of Bayesian analysis, prior distributions, posterior distributions, all that stuff. And then we talked in the second lecture about computing. This time I want to talk a little bit about model building, adding complexity of astronomical sources and instruments to models and how that works in a Bayesian setting. Oh, God. There it goes. And I'm going to go through some examples and some general principles and that sort of stuff. But let's start with a very simple example. It starts with recall, but this is something I skipped in one of the earlier lectures. And it's just a simple, what we call multi-level model. It's the simplest, maybe multi-level process in at least high energy astrophysics, which is accounting for background. But it illustrates kind of a more general principle. And so here I have at the top, you can see contaminated source count. So we observe Y, the total count, but we imagine that it's composed of 2 individual counts, source counts and background counts. We can't tell the difference, of course. So YS and YB are unobserved. Maybe we could call them missing data. But we only observe Y. There's another background exposure where we have a second count that is pure background, at least we suppose it's pure background X. And suppose we have a background exposure is 24 units. So what I'm going to do is specify my model in this kind of multi-level way, where at level 1, I'm going to condition on things like YB, even though I don't observe it. It's kind of like a parameter, like we're conditioning on the unobserved source intensity and the background count. And then I can say that what I observe follows a distribution that follows a Poisson distribution with the background, I'm sorry, the source intensity plus an additional background count. Okay. And then so I'm conditioning on these YB. And then at the second level, I propose distributions of things that I condition on. So at the level 2, I'm finding the distribution of YB, and I put X there too, because those are the things that depend on the background intensity. I see the background exposure is 25 times longer. Now I remember. So there's a 24 here just to indicate that 25 times longer, 25 more area, whatever it is. And then at level 3, we specify prior distributions. Again, so at level 1 and level 2, we're conditioning on lambda S and lambda V, so we specify these distributions here. Why do you do this? This is a very simple problem, but in more general, why do we do this is because it enables us to kind of conceptually think about the complexity one step at a time. So simplify the problem by conditioning on things, and then later in the model specification, specifying a model for the things we had conditioned upon. So a general definition, the multi-level is specified using a series of conditional distributions. The joint distribution can be recovered by the factorization theorem. So if I'm interested in the joint distribution of 3 pieces of data, for example, or unknowns, whichever, I can factor this distribution and then specify the models of each of these 3 things one at a time. In this way, we can combine models to derive an endless variety of multi-level models. So each of these things might be a regular standard model, but when I combine them in all different ways, I get all kinds of interesting, complex models that are not standard. So a little bit more involved example, again, from high energy astrophysics. This is a diagram of how you can conceptualize a spectral distribution, where at the very bottom here, this is our observed counts as a function of energy. At the very top is an idealized spectrum where we have an instrument that we don't have to worry about RMFs, effective areas, absorption, background contamination, or anything else. So the picture at the very top, we can specify a continuum and a couple of spectral lines, and the parameters that describe that are exactly what we're interested in scientifically. But then if we think about the instruments and actually other contaminants to the data, we can specify the distribution of the absorbed spectrum conditional on the true spectrum, the ideal spectrum, where in each bin we have a certain probability that a count is actually registered because it's not absorbed. I think we can conceptualize the effective area in the same way. Instrument response, or RMF, there's a blurring of the energy, so those two lines kind of look like one wide line. Pile up, I won't talk about pile up in any detail, but it's another kind of complicated process in the data collection. And so again, and then there's background contamination at the very end. So we can specify each of these things statistically one at a time, multiply all those models together, and get a distribution for our observed data. Okay, so let's look at, I'm going to go through some other examples in a little more detail how we actually deal with things. Probably can skip that. I want to think about selection effects. And this is an example we'll come back to later in the lecture if we have time in a more scientific way. But to kind of, again, to illustrate how this might work, suppose I'm interested in modeling the distribution of the absolute magnitudes of, say, type 1a supernovas. So we know type 1a supernovas have a common kind of genesis, and so their absolute magnitudes tend to be similar. But I want to kind of model that. But I only have data on the observable type 1As, which whether or not we observe it has to do not with its absolute magnitude, but its apparent magnitude. The difference between the apparent and the absolute magnitude is the distance modulus for nearby objects, and distance modulus is proportional to the redshift. For more distant objects, we need to think about the expansion history of the universe and dark matter and all those sorts of things. But generally, we're only going to observe M, say, if its apparent magnitude is less than, for example, 24, and then you can kind of go through. Capital M, the absolute magnitude is equal to the difference. We're only going to observe this if little m is less than 24, and so we're only going to observe the capital M if capital M is less than some function of little z, where that little z, f of f depends on the redshift and the relationship between redshift and distance modulus and the apparent magnitude. So suppose we're just going to use a normal distribution to model the absolute magnitude, and so we're interested in estimating mu and sigma, the mean and the variance of that distribution. But again, we're only going to observe capital M if M is less than some threshold, and that threshold is going to be different for each object. We observe for the observed objects, of course, we have redshift, or suppose we have redshift, and so there's going to be a different threshold for the observation depending on the individual objects. And so the probability for a particular value of mu and sigma, the probability that we observe a supernova decreases as its redshift increases. No surprise there. But we want to now account for that selection effect when we model the distribution. And how might we do that? Well, first of all, let's just ignore, as a baseline, let's just ignore selection effects. We're going to fit a normal distribution. How do we do that? Well, it turns out that, again, we talked about at the first lecture about these conjugate priors. Turns out there's a conjugate prior for the normal distribution as well. There's two parameters, so the conjugate prior is a little bit more involved. But if we have a normal distribution for mu, normal distribution for mu and an inverse chi-square distribution, so there's a chi-square in the denominator here, for sigma squared, the posterior distribution will have the same form. At least conditionally. So mu given sigma squared is also normal, and sigma squared given mu is also this inverse chi-square. Okay. So what this is they're conjugate conditionally. That's called semi or partially conjugate. And these semi-conjugate models work perfectly well if you're doing a Gibbs sampler, because in a Gibbs sampler you sample mu given sigma squared and sigma squared given mu. And each of those are going to be a standard distribution. So I say, see the next slide for the details. Let me just look at one of them again, because we've kind of talked about this sort of a thing. But again, for the normal distribution, you get the same kind of interpretation of the conjugate prior. So if we're going to build a Gibbs sampler again with simple, we're going to update mu given sigma squared, and that turns out to have a normal distribution with kind of this complicated mean and variance. And sigma squared given mu follows a known chi-square distribution. I guess one more slide where I have the actual, can talk about the details. If we update the mean, you can see that what we end up with is these are this is the average, well, the sum of the absolute magnitudes, which is, if you're estimating the mean, the way you usually would do it is a sample mean. So if you imagine there's an n in the denominator and the numerator that's canceled out, what we have is an average of the sample mean and the prior mean, and it's a weighted average, where the weight here is 1 over tau squared, and the weight here would be sigma squared over n. Sigma squared over n is the variance of the sample mean. So if the variance is bigger, we're going to downweight it. If the variance is smaller, we're going to upweight it. And similarly, we're going to weight the prior mean by its variance. So it's a variance weighted average. You can come up with a similar kind of explanation for the variance of that distribution. Maybe we shouldn't worry about that. But you can set reference prior. So if you set mu0 equal to 0 and you set tau squared equal to infinity, that's really for over here, you end up with just the standard normal distribution summary statistics feeding into the posterior distribution. So then the posterior distribution of mu is centered on the sample average of the data. Okay, so you kind of you take that prior distribution, you make it go all the way to being a flat distribution, and then only the data matters. Okay, so there's kind of a standard distribution. I'll leave you to look at the slides if you're interested for this. You can make a similar argument and come up with a similar reference distribution for the variance. Which is also a flat, in this case, it's flat distribution on log sigma squared. Okay, so that's the kind of the ignoring selection effects. You can just fit a normal distribution in the regular way. If we want to account for selection effects, I'm using this capital O to indicate whether or not the data is observed. So if O is equal to 1, I observe it. If O is equal to 0 or not equal to 1, I don't observe it. And so I want to find the distribution of the absolute magnitude given that it's observed. Okay, so that's the notation on the left, the distribution of M given O is equal to 1. And how do I do that? Well, that's going to be Bayes' theorem. So this is the marginal distribution of the absolute magnitude given the parameters. And we're going to say we always observe redshift, so that's fine. And then this is the distribution that I observe it given M, the absolute magnitude and the redshift. And then the denominator, I'm just normalizing that thing to make it actually a distribution. And that integral, you can't forget about the integral in the denominator because it's going to depend on sigma, theta. I'm sorry, the parameters that describe the distribution, so the mean and the variance. And so here, in this particular example, we're modeling the marginal distribution of the absolute magnitudes as normal. The conditional distribution, if I know both M and Z, well, I know exactly if it's going to be observed or not, whether or not based on whether M is less than F of Z or not. So this turns that means that this thing is going to be 0 or 1 if Z is fixed, depending on the value of capital M. So it's what we call a truncated normal distribution. We have a normal distribution, we just truncate it at some point. And in this case, that truncation point is going to be different for each object depending on its value of Z. So it's not just a truncated normal distribution, but the truncation points are all going to be a little bit different. Now I'm going to use the same prior distribution. Now, because I no longer have a normal distribution, things are not conjugate. I can still kind of use a Gibbs sampler like I was doing in if I ignore selection effects. The problem is that mu given sigma squared is not a normal distribution, and sigma squared given mu is not an inverse chi-square distribution. They're not standard distributions because of the truncation, but I can do a random walk metropolis using proposal distributions like we talked about last time. Simple thing we could do. You could also do something jointly on the, instead of doing the Gibbs version, you could try to sample them jointly, would also be fine. But just because we started with Gibbs, I kind of continued with Gibbs. So now let's see what happens. So this is a simulated data set. So there's the true values of mu and sigma squared for my absolute magnitudes are for a sample size of 200. I'm going to sample Z from some reasonable distribution for each. So I'm going to put my supernovas, I'm going to place them in the universe with more of them more distant and fewer of them nearby via that distribution. The black line is the f of Z. And so I observe the supernovas if their magnitude is below the line, and I don't observe them if they're above the line. And so what I'm going to do is see how these algorithms work. In the first case, so yeah, model 1 is just ignoring selection effects. The red line is the truth. This is the mean. Should be, yeah, mu0, I guess, is the mean. And log sigma squared is the variance. This is if I just ignore selection effects, and this is if I account for selection effects. Now, in this case, the distributions capture things in both cases, but you can see, generally speaking, I'm going to end up underestimating mu. Now, it's a little hard to say generally speaking, because we only have one instance here. But if you think about it for a moment, you can convince yourself that it is generally speaking, because we're, whatever this curve looks like, we're going to be disproportionately missing some of the more some of the dimmer supernovas. So we're going to the scale is confusing, but you're going to have more values that are lower. So we're going to underestimate the absolute magnitude. So now if I redo the simulation, but I'm going to redo the simulation with a higher variance. So instead of having sigma 1, oops, now I have sigma 3. So the red up there has changed. So the distribution is just wider. And so what that means is there's going to be more supernovas that are above the thresholds. They're not observed. And we get, a more significant bias. Okay. So this is all, selection effects, something you absolutely need to be consider when you're doing any kind of population study in astronomy. If you're looking at individual sources, you don't kind of have to worry about it. You're just learning about that source. But if you want to think about the distribution of some property across sources, selection effects are always going to be an issue. More distant objects are less likely to end up in your data set. So what this is trying to illustrate in a simple problem is one way you can deal with selection effects from a Bayesian point of view is think, how would I do my analysis if there were no selection effects? That's level 1 of my model, right? I think about an ideal situation where I have the full population, and then I layer on top of that a model for the selection effects, in this case, whether or not capital M is less than f of z. And I incorporate that into my model and I adjust. Okay. How I do my model, how I do the computation and everything else. Okay. There's kind of two main themes in this set of lectures, I guess, at least the first part of it. One is multi-level models, and that's kind of what I was describing before. You specify conditionally, you say, you imagine, how do I observe if they're observed, and then how do I model the probability of being observed, for example. And the second one is what are called hierarchical models. And in hierarchical models, again, I'm thinking about cases where I'm looking at a population of sources. I can do the analysis of each individual source. And I then want to look at the distribution of sources. So how does the magnitude, in the example I had a moment ago, is kind of like this, right? How does the magnitude of this sort of object vary across the population of sources, and how can I kind of incorporate that into my model? What astronomers will often do is they'll do all the individual studies, and they'll make a plot of the fitted values for all the individual studies or individual sources, maybe with the little error bars, and then kind of look at the distribution or maybe summarize the distribution. What I'm going to argue is that you shouldn't just do those individual analyses. You should simultaneously account for the fact that you're doing multiple analyses, and that those multiple analyses together teach you about the population. So that's the goal. So let's think about a simple case here. Suppose you want to estimate a parameter theta from repeated measurements. So just one parameter I want to learn, but I have a repeated measurement. Suppose I'm trying to calibrate my detector. So I look at a particular source multiple times. I want to make, I want to see if I get the mean is equal to the true value and how much variability I get between observations. So I'm interested in estimating theta. Maybe I know about sigma squared already, or maybe I want to estimate that as well. But we're focusing on theta. So I have multiple observations from the same object. The obvious thing to do to estimate theta is to just average the data. Who's gonna argue with using the average to estimate the parameter? Well, I have the superscript naive here, which is a hint that it turns out that this is not necessarily the best way to go. So let's see why is it that you might not want to use that sample mean? So how do statisticians typically, this is really a frequency analysis, how do statisticians evaluate an estimator? Well, you usually want to have, it's not so different than the kind of things you do in machine learning, right? You start off with some kind of loss function. So, I'd like the theta is the true value, theta hat is my estimate. I want that to be small, right? That's it's a loss function. How far do we expect it to be? Well, then we can take the average loss, sometimes called the risk, or with this particular loss function, it's called the mean square error. So for every data set, I'm going to get a different value of theta. This is the truth. So that this doesn't change if you're a frequentist. This is the mass of the star, whatever it is. I have multiple observations. Different data sets have their own statistical errors, so they're going to move around and the estimates are going to be slightly different. So I take the expected value across multiple data sets. And this notation writes that out a little bit more clearly. What's random here, the distribution I'm thinking about is the distribution of how the data varies from observation to observation. So this thing moves around, it's random. I want to find for repeated frequency, repeated observations of my data set, how far off do I tend to be? This is called the mean squared error, MSE. And it turns out there's a definition. An estimator is said to be inadmissible if there is another estimator that's always better. So notice the mean squared error can depend on the truth. Right there, you could find, I'll give you an example in a moment, where depending on the true value of the parameter, you'll get a different mean squared error. But if you can say for any value of the parameter, I have an estimator that's going to give me a lower mean squared error, well, I should use that one. It sounds like a better estimator, right? And we say an estimator is inadmissible. If this is true, we should never use this estimator. It's inadmissible. We should use this one instead. It doesn't, incidentally, you don't have to use squared error loss. You could use a different loss. You still call it inadmissible. But just to make things simple, I use the kind of the most obvious thing, squared error loss and mean squared error. Okay, so let's look at an example. This goes back to this binomial example we had in the lecture the first time. So I have a binomial data set, and you remember we're using the binomial for hardness ratios, but we won't think about the precise example in this case. I have a binomial distribution. I still have the capital H for hardness, and I put a beta distribution because it's conjugate, and we found out that the posterior distribution also is beta again because this is a conjugate distribution. And one way I might estimate success, that pi, is by the posterior mean. And if I use different prior distributions, I'll get different posterior distributions, and they'll each have their own mean. There's also the MLE. If I want to know the probability of success, I've observed n objects. How many of them? In this case, it was 3. how many of them had a hardness ratio, were hard sources, I should say, and just look at the proportion, H over N. Okay, and so I want to compare those things, and I can do that. Oh, before I should have done this in the other one. So this is again, let me go to the finish the example, and I'll come back to this more general talk. So this is the mean squared error of those four estimators. So the solid line is the MLE. The dashed line, this one, is if I have beta 1, 1. And so what that means is instead of doing the number, let's imagine we're flipping a coin. It's a little easier to think of, but I flip a coin 10 times, and I have, the number of successes. I want to see if it's a fair coin. So I take the number of successes over 10, that's the MLE. Beta 1, 1 says I take the number of successes plus 1 and divide it by, instead of 10, I divide it by 12. Seems a little strange. And these other ones are doing similar things. I add 1 to the number of successes and I divide by 14, 10 plus 4. Here I add 4 to the number of successes and divide, I'm sorry, not 14, 15. They have both of those. Okay, so why would, and you can see when you do that, well, let's not worry about that. It's not quite so clear as I thought. But if you look at the mean squared error, so particularly this one, you want mean squared error to be less. The MLE, the obvious thing that you would always think about, the number of, if you flip a coin 10 times, you get 4 heads. Your estimate of the probability of giving a head is 40%. That has significantly higher mean squared error for a big range of the true value of the probability than adding 1 to the number of successes and failures. Now, especially because most of the time when you're trying to do something like this, you're not really thinking about cases where the probability is very close to 0 or 1. Usually, it's something kind of a little bit more subtle where you're really not sure. Does everyone agree? If you're doing a population survey, if the probability that people agree with the government, whatever it is more than 95% or less than 5%, you're not doing a survey. Just by talking to people on the street. The cases you're interested in are the cases in the middle. And if you're in the middle, you shouldn't be using the MLE. Now, in this case, there is not, and it is not inadmissible because there are parameter values where this one is better. There's other parameter values where this one is better. Right? So these are a little strange. You'd have to think, if you really thought it was likely to be something near 0 or near 1, you might want to use one of these. But as just a general estimator, and if you look in elementary statistics books now, you'll also find people talking about adding 1 to the number of the number of successes and the number of failures before you estimate your estimation. So now going back to this slide here, just a little bit more how frequent is to evaluate estimators. There's something called the bias. This is again on repeated simulations. I repeat my experiment many, many times. I find the average of my estimator. If that differs from the actual value, that's called bias. We'd like on average to get the right answer. The variance is the distance from the average of the distance from between the estimator and its mean, just like a variance. And the mean squared error combines those two things. So if you have just the word bias is bad. Nobody likes biased estimators. Nobody likes biased people. Nobody likes biased anything. Bias is bad. But the word bias might not be, it is kind of what it is. We want to be a little careful in a statistical context. That bias is not always a bad thing. So if I have a biased estimator here, this is the truth. This is the distribution. If I repeat it, it's off. For it to be unbiased, the mean has to be right on top of that red line. It's not, it's a biased estimate. But if I have a choice between this estimator and this estimator, which is unbiased, but very variable, it tends, even though this one is systematically off, it still tends to be on average closer. So in mean squared error terms, when I combine both of them, you would find that this is a better estimator than this. So bias, all things being equal, bias is bad. But it's probably good to look a little bit more holistically at an estimator before you just look and say bias bad. Think about variability as well. And there's a very standard concept in statistics is the bias variance trade-off. Usually we expect that if you add a little bias, you can bring down the variance, or vice versa. And so there's a trade-off between these two things that the mean squared error tries to settle. Okay, so let's go back to the original problem. We're trying to estimate an average. And I'm going to change the original problem subtly, which changes how it works enormously. So here, I wanted to estimate one quantity theta, and I was thinking about whether or not I can use an average to do so. What I'm going to do now is instead of trying to estimate one theta, I want to average capital G theta. So I have the G are groups. Maybe that's not the best notation for an astronomical. Maybe we should use S for sources. So we have a bunch of independent groups. They each have their own value of this parameter. And for each of them, we want to estimate their population mean. Okay. So, you know, the average age of stars in a globular cluster. You have G globular clusters. There, G works again. G globular clusters, and you want to estimate the average age of stars in each. Again, the naive estimate would be to say, so in this case, the I indexes capital N, a very large number of stars in each globular cluster. So if I wanted to find the average age for globular cluster J, I could just average this across the stars in globular cluster J. Turns out that this is inadmissible if I have more than three or more. So if I just want to estimate one parameter or two parameters, the sample average is fine, but three or more, there's a better estimator. It's called the James Stein estimator, name for these two kind of statisticians, James and Stein. And they showed that this estimator, JS for James Stein, dominates, that is a smaller mean squared error for all values of the true parameter. And what did they do? Look, let's take it apart a little bit. This is that sample average we had there. So it's a weighted average of just a regular sample average and any other number. Any other number. This is like bizarre that this is going to be better than the sample average. And it's a weighted average. So this is going to be a number between 0 and 1. So I'm just have a weighted average of those two things. And how do we, in the weight is written down there below, you can think of, okay, sigma squared over n is the variability of any one of the estimators. So if the variance is very large, this thing is going to be close to 1. So if I have very noisy estimates of the individual parameters, it's saying downweight them. If that seems sensible, maybe not to just nu, but if you have noisy estimators, downweight them. And the other thing is this tau. If it's very big, I'm going to, or say very small, then this becomes close to 1, and I want to use this as well. What's the tau? It's the average distance of the thetas, the individual parameters from nu. So if the thetas tend to be very close together and close to nu, well, use nu. That makes sense. Okay. So let's look at an example. And so this is that James Stein estimator. And these are called shrinkage estimators because of plots like this. So as that weight changes, we have the individual groups, and they're each going to have their own estimate, just their own sample average. And as the weight goes from 0 to 1, I go from the individual estimators to nu. And we're going to be over here. If the individual estimators are precise, so sigma squared over n is small, or the estimands, the thetas, are very different, that if that tau squared is big. And I'm going to be over here if the individual estimators are really noisy, or I know the true values of the parameters are very close to nu. So where should we shrink? So nu, you know, the true value, what value of nu should we use? Well, maybe I won't worry about this slide so much, but you can kind of see it in this picture. The value of nu that you want to use, the best value of nu, is the average of the thetas, right? So if you want the variance, if you want this thing to be small, the way to make this thing small is to make nu equal to the average of those things. So we want to, the best thing we end up doing is taking, so what you're going to do is you're going to take a weighted average, still here, the weighted average of the individual globular cluster parameters, estimates, and the average of all globular cluster estimates. Okay, so let's go through, let's see how this works. This is just a little simulation study, so it's just normal. So the y's follow a normal distribution with theta j, and the theta j are evenly distributed between 0 and 1. So what's important here is the theta j, the individual parameters are very similar. So the mean squared error of the ordinary average is up here. But if I shrink towards the average of all of them, I do much, much better. My average error gets cut by 60%. And the reason it works in this case is that the truth values are all very close together. And if that's not the case, now I have the true values are evenly distributed between -4 and 5 over this whole range, then shrinking towards this value doesn't help me very much at all. So if I know the population is homogeneous, these shrinkage estimators tend to do a lot of help. But if it's not homogeneous, it tends not to do so much. Okay, so intuition. Why this is a sensible thing to do? So this is the first thing. It's not really intuition. It's just if you are it's just the fact. If you're estimating more than 2 parameters, it's always better to use shrinkage estimators that shrink towards the average of the parameters. You get the most gain when the individual estimators are noisy or the population is very homogeneous. Bayesian versus frequentist. From a frequentist point of view, this is somewhat problematic. What's problematic from a frequency point of view is that all of these things I'm saying, what depend on the true values of the parameters. If the globular clusters are very homogeneous in terms of their parameters, well, how do you know that in advance? Well, if you're a Bayesian, it's exactly what we do. We say, well, what do you think about these parameters, right? Before, that's what prior distributions do. So from a frequentist point of view, it's an opportunity. From a Bayesian point of view, it's an opportunity to get more mileage out of your priors. From a frequentist point of view, it's like, but I don't know. And I should say, James and Science, it's maybe the biggest breakthrough in statistical thinking in the last 100 years. Just for them to stand up in the 1950s, 60s and say the sample average is inadmissible. You shouldn't use the sample average if you're estimating more than 2 parameters. It shook the statistical world. And it's still kind of astonishing. From a Bayesian perspective, so this is the kind of things I said before, is that these basing things on values of parameters is kind of fine. So let's so this is now what all the things I was describing before were completely from a frequentist point of view, right? We're computing the mean squared error. We're trying to minimize the mean squared error. I didn't show you any of their calculations. Their calculations went on for pages and pages and pages. Now let's just do the same thing from a Bayesian point of view. It's going to be a hierarchical model. I have my individual stars and my individual globular clusters, and I'm interested in their mass or magnitude, whatever it is. It's not magnitude, it's their mass. And I'm interested in the average mass for that globular cluster theta j. And these are all globular clusters. They're all globular clusters around the Milky Way, our own galaxy. So, they're a population. It makes sense that they're not completely different. So we're going to say that the theta j's follow a population distribution. That's a hierarchical model. So we have the individual stars being modeled given the globular clusters, and here hierarchically, now we're modeling the globular clusters. What is the mean age? I keep changing what it is. Well, so the mean age of stars in that globular cluster. How old are globular clusters across the Milky Way? A bunch of parameters, we have to put priors on them. But if I want to estimate this parameter here inside of this model, the expected value, that's the way we usually estimate a parameter, given the parameters of the data, well, it turns out to be exactly the Bayesian analog of James Stein. It's the average of the individual estimator. And this kind of a thing, it's, when we did the normal distribution, remember the posterior distribution for a normal is a weighted average of the data and the prior. This is the data, this is the prior. Now, because it's a hierarchical model, though, this mu is fit to the data, right? It's a parameter, it's not just some prior distribution, it's a population distribution. So it's going to be an average of the mean of the average ages of the various globular clusters and my estimate in this individual one. So everything just falls into place. You don't have to be a genius. You just write down the distribution and compute the posterior distribution. And that's what James Steininger did 60 years ago. And we're absolutely, they were geniuses, but they did it without the guidance of Bayesian thinking. Automatically picks the best value of mu. It's the mean. Provides model-based estimates. All those parameters that we were worried about before, like how much shrinkage depends on all these things. They all get estimated along the way. Does require prior distributions, of course. And the other thing is that, this is the normal model, and they did their analysis inside of normal models, essentially. But I could use Poisson models and gamma distribution, whatever I want, and I still get this kind of shrinkage and this kind of optimality kind of automatically by doing following the Bayesian model. Okay, so let's look at a little bit more of an astronomical example. I was talking about supernovas before. I'm getting a little closer to the actual problem now. There's this thing called the color correction. So you imagine you have a time series or a light curve of a supernova as it's exploding in multiple photometric bands. The importance of the color correction will come up when I get to the full example later in the lecture. But for each supernova, we have what's called a color correction, which is essentially looking at how those light curves, maybe it's first in the blue light and then the green light and then the yellow light. There's kind of like accounting for how that supernova explosion progresses through the filters. And it's some statistic that astronomers have come up with to measure that. Okay. And so for each supernova, I have an estimate of it. It has an error around the true color correction. So I'm going to say this is known, like this astronomers often will. I have an estimator, I can say something about it. An estimate, I can say something about its errors. It has a true color, but it's different than the true color correction for that supernova. And these supernovas have a distribution. So this is a hierarchical model. So the true color correction follows a normal distribution that has some mean and some variance. And so this, in this setting, I'm going to say this is known. So the only two parameters are the mean and the variance of the population level color correction. And I could, and what you might often do is, well, for this particular supernova, I have an estimate, C hat, and I have a sigma j for it. So I can just take that, my estimate, and say it's the color correction plus or minus sigma. And I'm going to say, unless you only have two supernovas, don't do this. Okay. And so how are we going to do it? Okay, so we're going to fit a give sampler. I don't want to talk too much about the algorithms. It is kind of nice. Is it going to be important later? Maybe. Probably not too important. It's kind of maybe a little standalone. But what happens is in this kind of hierarchical model, I end up using that conjugacy of the normal distribution twice. So I'm going to have a give sampler. So in the first instance, I'm going to suppose I know C0 and R. So I know these two parameters here. So if you look at that with these two things known, that's just a normal distribution with a normal prior. So that's the conjugate distribution. So I can sample from the posterior distribution. Oh, I'm sorry. I'm just writing this thing down again. This is the likelihood, has a normal prior. That's a conjugate distribution, so I can sample once. And then the other step, I'm going to say, instead of saying these things are known, I'm going to say all of the CJs, all of the true colors are known. And then I have a normal distribution for the colors and a non-informative reference prior on the parameter. So this is another normal distribution that's conjugate. So I use one conjugacy and then another conjugacy, and I go back and forth between the two. So it's really easy to set up a nice algorithm. But again, that's there's all the details. Okay, let's leave that alone. But let's focus on the shrinkage aspect of this. So you can see shrinkage from this picture. And remember, what determines the amount of shrinkage is how variable the individual estimators are and how much homogeneity there is in the population. In this case, I'm going to leave the individual estimators alone, and I'm going to just look and see how these estimators vary depending on the homogeneity in the population. So this RC, remember, this is the variance of the true Cs, the true color. So how much variability there are in this color correction among supernovas. So if I say this variance goes to 0, so what I'm saying there is that all supernovas have the same color correction. If all supernovas have the same color correction, and I know that, well, they should all have the same estimate. And so that's what's happening here. Over here, I'm letting this thing, it only gets up to 0.5, but you can imagine it asymptotes, it kind of goes all the way up to infinity. These little pluses are the C hats, the individual estimates of the color corrections. This gray bar is now I fit my hierarchical model, and I have the posterior distribution of RC. So my estimates are going to be, an average across this little bar. So these are where my true estimates are. Or my actual estimates are the shrinkage estimators. You can see why they're called shrinkage. They go quite a bit from the original data estimates, but they don't go all the way to saying they're all the same. Now, this picture I think is really informative for understanding a little bit of intuition. If all of these plus signs, they're noisy. They have errors in them. And if you just have this one all by itself, is its error up by 1 standard deviation or down by 1 standard deviation? Of course, you don't know. If you knew if the error were more likely to be positive or negative, you would adjust your estimate. You don't know. There's estimates that can be positive or negative. You don't know which it is or equally likely. But if you look at them all together, and they're from a population of similar types of objects, they're not going to be all the same, but they are similar. And you just look at this distribution of pluses, ignoring everything else. Is this one more likely to have a positive or a negative error? It's more likely to have a positive error because you know the distribution across the sources. There's real information in that distribution, and it's telling you that this error is more likely a positive error, so you should estimate it to be something smaller. This one's more likely to have a negative estimate. Is it an outlier? There's two reasons that these values are extreme. One is that it's actually a little bit more extreme of a supernova than the rest. And the other possibility is you've got a little statistical error in that direction. And by looking at the distribution together, you can learn, and you don't have to think too much about it. You just have to do, we say turn the Bayesian crank, write down the appropriate model and see what the posterior distribution tells you. But the reason the posterior distribution is telling you that you should shrink in this way is because it's kind of learning that these are more likely to have positive errors, these are more likely to have negative errors, and it's adjusting appropriately. And you're fitting all the variances along the way to kind of know how much you should adjust. Okay, so these are the fitted values, the C's. There's also the plus or minus sigma. This is the plus or minus sigma. So same thing, basically the same plot. If in this extreme case, if all of the supernovas had the same color correction, then you would just, if you knew that, then you just take all the data and do a single analysis. You have a much bigger data set. It looks like the standard error is 0, but it's not. It's just, you have a much bigger data set. I had plotted, this is, I should say that this is an analysis of some thousands of supernovas. I don't plot them all here because it would make the plot unintelligible. But if you combine the data from 1,000 supernovas and you assume they all have the same color correction, you'd have a huge data set and the standard error would be very small. And these are the standard errors, the plus or minus sigmas from the original analysis, that if you just had one supernova by itself, what you would use. And again, so what you're essentially getting, not only because from learning from the population, you're also getting reducing the uncertainty on the individual estimates significantly, especially the ones with the big variability. It gets pulled in all the way here. They still won't have the same variability, but the variability will be significantly less. Okay, so what do we want to say here? Oh, okay. Maybe just a summary. That's James and Stein had to find their estimator. I mean, so this is also, so even if just a little insight into how statisticians think here. Even if you are a die-hard frequentist, you don't want to ever write down a prior distribution. You don't ever want your analysis to be based on this kind of subjectivity. You might still use Bayesian thinking to come up with your estimator. And then, use Bayesian thinking to come up with the estimator, the functional form, and then throw away all your prior distributions and just use that thing as a statistic that you're using to make an estimator. So one thing I like to say is, frequency analysis, if you go back here, frequency analysis tells you how your estimator should behave. You want an estimator that has smaller bias. You want an estimator that has lower variance or smaller mean squared error. But what is that estimator? How do you find that estimator? Frequency analysis tells you nothing about that. It tells you how to evaluate an estimator, not how to find an estimator. Bayesian analysis, on the other hand, is completely opposite. It's completely agnostic about how to evaluate an estimator, at least in the most obvious way. You have a prior distribution, a likelihood, you multiply them together, and voila, there's your posterior distribution. Your estimator should be based on that. Is it a good estimator or a bad estimator? Was your prior good or bad? That's as much, or maybe you misspecify your model or something like that. But basically, Bayesian, at the basic level, Bayesian estimators are telling you how to find an estimator. Frequency analysis is telling you how to evaluate an estimator. Those are not contradictory tasks. You need to do both of those things, right? They're both good things to do and to think about. So even if you're completely a frequentist, you may well use Bayesian thinking to derive your estimators. Like James Stein didn't, as far as I know. Maybe they did. I don't know. But they justified it completely from doing the hard calculations, not from using the Bayesian. Bayesians have methods. I think this is what I just said. Bayesians have methods to generate estimators. Everyone likes this. General principle is easily tailored to any problem. You can write down the hierarchical model and just follow Bayes' theorem where it takes you. Specification of the level 2 model may not be critical. That's so one thing people often complain about. So the level 1 model, that's a Poisson distribution if you have counts, or it's a Gaussian distribution if you're looking at optical data, right? It has to do with your detector and what kind of errors you have. That model's kind of fine. People don't usually argue too much about it. That level 2 model, though, now I'm going to put a normal distribution on the average mass of globular clusters. Well, maybe I should use it. Maybe that's important. Why do you think it's a norm? All these kind of questions come up because we don't really know. That's a much more science question. But one thing that's worth noting is I wrote this all down in terms of normal distributions, but James Stein did this all in terms of moments. So expectations, variances, mean squared errors. They didn't have to make those normal assumptions about that distribution. They still got these estimators. So you can tear back a lot of those assumptions and still find the same thing, same estimators are the right things to do. Yeah. This is just maybe, it's probably worth, how much time do I have? I have a little time. It's probably worth mentioning this. This is the most prominent example of where you have to be careful about using improper prior distributions. So I'm going to just do this briefly because we didn't go through all the details to have the background, but maybe I can just go back. Yeah. It's this one. So, the way that you can kind of come up with a improper prior distribution that's okay. You have this conjugate prior, you have the likelihood, you multiply it together, you see you have you know, this is the variance of the data around its mean. And then you take the weighted average. This is a chi-square with n plus nu degrees of freedom. If you make nu equal to 0 and beta equal to 0, now I just have the variance, like, you know, the variance divided by some, you know, it's the sum of the squared residuals divided by something that has expectation equal to n. That becomes very kind of a natural thing to do. I don't have to worry about a prior distribution. I make beta 0 nu, but everything's fine. I can see it's a proper distribution. Then I look and I say, if beta is equal to 0 and nu is equal to 0, that corresponds to putting a flat prior on log sigma squared. Sigma squared is strictly positive. Take the log, that has a value on the whole real line. Seems completely sensible. Unfortunately, that was fine, and it works in that problem. But if you just say, if you cut corners and don't do that analysis, you can get yourself into trouble. So this is now the Gaussian hierarchical model. So I have a normal distribution at the top that say sigma squared is known, and I now put a prior distribution on theta j, and I estimate mu and tau. I'm learning about the population. Now I have a mean and a tau, a mean and a variance. I might just put that same prior on. It worked fine when it wasn't a hierarchical model. It looks a lot like it. Why not do it? Well, it turns out that prior distribution is 1 over tau squared. Flat on log is on the variance scale 1 over tau squared. And if you look at the posterior distribution, you think about what happens if this thing at tau goes to 0. This is not a proper distribution because 1 over x is not integrable from 0 to infinity because it blows up at 0. And if you look at the posterior distribution, if tau squared goes to 0, all of this stuff, because it's something plus tau squared, something plus tau squared, this goes to a constant. Near 0, this is just a number. Near tau squared equals to 0, this is a number. And this thing near 0 is going up to infinity, and I get a distribution that doesn't exist. So just using what seems to be a completely natural prior distribution because of the standard simpler model in this slightly more complicated model leads you all kinds of problems. And, you know, there's a bunch of papers from the 90s where people were using this wrong prior and getting weird results. And it's, now you look at it like, well, of course, this is a constant, you multiply by something that's not integrable, it's not going to be integrable, it's not a distribution. But if you don't take the time to look at that, you can get yourself into trouble. So if you don't want to look at it and think about the mathematics to make sure it's integrable, somehow use a uniform prior, do something with it. It's much better to use a uniform prior than to use an improper prior and not check it, because you can really get really strange things in that case. So it turns out for this one, you use a flat prior instead of on log, you use a flat prior on standard deviation or square root, and then it's fine. But you have to do an analysis to verify that. Okay, so now I want to do something a little bit more complete with the supernova data in the last bit. This is the same slide as we had before, except at the bottom here, before I was talking about when I observe the capital M and when I don't, because I have this truncated data set, et cetera. Now at the bottom, I say, if we observe both the apparent magnitude and the absolute magnitude, we can infer the cosmological parameters, because M minus mu, the difference between the absolute and the apparent magnitude is equal to the distance modulus, and the distance modulus depends on these parameters I might be interested in. So if I knew both little m and big M, I could estimate those parameters. Of course, little m is easy, and the apparent magnitude I can measure. Absolute magnitude, how do I measure absolute magnitude? Well, that's where the supernovas come in. Maybe you all know about this very, very famous Nobel Prize winning kind of use of supernovas. But these type 1a supernovas, you have a white dwarf that's happily living its life and no big deal. But there's a maximum mass for white dwarf stars to be stable, but they don't have any way to gain mass all on their own, so that's okay. But if something comes near it and mass accretes onto that white dwarf, it can break that Chandrasekhar limit, and then there's that's a type 1a supernova. So what's very important, of course, is that because they all have the same genesis, they were at a particular mass, they broke the limit and they blew up. They're very similar in their absolute magnitude. So they have an absolute magnitude distribution. Normal is not so important. What's important is that this intrinsic variability of the absolute magnitudes is very small. So we can think of this thing as just a nonlinear regression. This is observed data. There's this crazy nonlinear function, depends on the parameters we're interested in, plus Gaussian error. Not mean zero, but I can take out the mean. And if you're doing regression, statistical thinking, right? You know, you're going to get much better estimates of your parameters if the residual variance is small. If the data fall close to the line, you can estimate the slope. If the data is all over, the slope estimate is going to be very wobbly. So, you know, that's the idea. I don't want to go into the details of this too much, but this is where that color correction, there's two things, the color correction and the stretch. And basically, gosh, there's a lot here. Maybe we can just look at the bottom. We have the same model. If I add covariates, so this is the color correction, this is the stretch, that's just how long does it take you to stretch out the light curve to match a template, how much do you have to stretch it? If I add these covariates, just like again, in any statistical regression, if you add more covariates, fitting a line to more variables, the residual variance can only go down. So these variables, you know, people have found to be related. There's a little picture. This is the stretch and the peak magnitude when you can measure it, and you can see there's this correlation. So you can suck up some of the residual variance to get a little better estimate. That's more about this. Yeah, it's a kind of interesting and important, but not exactly relevant to the lecture today. I'm showing this a little bit. Now, this is the hierarchical model. So the hierarchical model becomes more interesting and a little more complicated because of the color and stretch. And we have a model that looks, it's a more complex version of the model I had earlier, where you can see C hat is normal C, but I also have the stretch and the absolute magnitudes, and there's this is a covariance matrix that is known, the variability of the individual estimators. And I put a hierarchical model on both the color and the stretch, and for the magnitudes, I have this kind of nonlinear regression. But it's a hierarchical model, and so we end up seeing some of the same features. Now I'm estimating that this is, you know, the only reason really to show this is because this is actually, you know, the science. The conditional posterior expectation of the absolute magnitudes of the supernovas. Again, there's thousands of them, but we have a selection of them so you can kind of see what's going on. I don't have the truth here because I don't have the truth because it's not kind of, I don't have that C hat. It's not a direct estimate of the conditional expectation. But you can see the shrinkage. This is the posterior of the variability, the intrinsic variability. And the errors also, you get the same sort of thing, kind of significantly better estimates of the individual magnitudes by analyzing them all together. I kind of lied just a moment ago when I said we don't have estimates. We can take this whole model, same model, and try to fit it without shrinkage. You know, we estimate the parameters by chi-square minimization. We know H naught. We don't do the hierarchical model for these parameters, but just treat the observed values as true values. So it's a little hand wavy. Is that what you would really do? I don't know, but it's a reasonable approximation trying to do this estimation without the hierarchical model. And you can see these are, again, a selection of these objects at different redshift, and the little whiskers are the uncertainty, and the blue dots are the estimates. The blue ones are from the Bayesian analysis, and the red ones are without the shrinkage. So you can see that the Bayesian estimates shrink it and the errors get smaller. So that's kind of nice. Let's not worry about that. The last thing, how much time do we have? Oh. Yeah, I guess I can go like another 10 minutes. I'll go through it relatively quickly. Or is it better? Do you have questions? Or do you want one more little barrage of statistics? this last piece is how machine learning mixed inside of Bayesian analysis. So it's kind of cool. To do that analysis of the supernovas, maybe this is a better picture. We need to know which supernovas are type 1a. Otherwise, it's a mess, right? You need to know the type 1a supernovas. Spectral analysis, if you have spectral data, that's easy. Lots of times now, of course, people have only photometric data, and you want to try to estimate from photometric data whether or not something is a type 1a supernova. And the way to do that is to build a lovely machine learning algorithm. You train the data on the spectroscopic data because you know which ones are type 1a from the spectroscopic data. But once you have the trained algorithm, you can then deploy it on the objects where you only have photometric data and decide which ones are type 1as. That's all fine, except for one little fly in the ointment, as that these two data sets are quite different. Spectroscopic data, we tend to have a lot more nearby low redshift, but we're interested in distant high redshift, dimmer objects. So if we train on these nearby objects, are we going to be biased? So this is trying to get at that. So I don't, this slide is summarizing. This slide is summarizing how you do the classification of type 1a supernovas. You have these light curves that are kind of observed at regular times and all of that kind of stuff. Let's not worry about that. That's a machine learning specific question. What I want to focus on instead is how do I account for the fact that my training sample is different than my test sample? So this is just showing you that the training set is different from the test sample. This is, the distribution of R-band observations for the photometric is the solid and the spectroscopic is the dash. So the spectroscopic are lower magnitude, so nearby objects. The colors aren't quite so bad, the differences, but the individual magnitudes are quite biased. Yeah.
Well, the distant objects, not only are they fainter, they are redshift.
I don't remember what I said, but yeah, the distant redshift objects, fainter, are less prevalent in the training set. Spectroscopic data, yeah, absolutely, yeah. So this is just a picture. There was a challenge that was put out for this data set, for this particular problem. So this is from the challenge. But the general problem we're trying to address is what's called covariate shift. So I believe that for the training and the test set, the conditional distributions are the same. So whether or not something is a type 1a, depending on its photometric magnitudes, that's the same for the two. The relationship between the variables. The problem is that I have a very different distribution of the trainings of photometric magnitudes in the training test set. This is you can see the gray ones are the photometric data, and the colored ones are the spectroscopic data, type 1a and not type 1a. And you can see it's a little hard to see. There are blue and orange points down in here, but not very many. So what we do is take a page to address this, a page from causal inference. So causal inference is a statistical kind of pursuit where you have observational data and you want to try to learn causal relationships. So we split the, you imagine you imagine you are trying to figure out if smoking causes cancer, and you have people who smoked or smoke and people who don't. And you find that the people who smoke have higher cancer rates, but there's also all these other differences. There's different socioeconomic classes, there's different age distributions, there's different gender distributions. They might have more working class jobs where they're working in factories and in places that might also have bad effects. So that's to say, the distribution of the treatment group, the people who smoke, is different from the people who don't smoke in these terms of these covariates that I'm trying to use to do the prediction. So propensity scores is a technique for in those sorts of settings to do what we call balancing. So you find out you estimate the probability that you're in the control group or the treatment group, whichever one you want to define it. So we'll say the treatment group, given all of the variables that you have. And what, so that's a probability, you're going to estimate that. And what these guys showed was that if that condition on those propensity scores, the distribution of the covariates is the same. So it's called a balancing score. And if I can compute it and condition on it, I can remove this kind of a bias in my data. So let's look at how it works in machine learning. We want to predict y from x, so whether or not it's a type 1a from the photometric magnitudes. We have a predictor function, that's going to be my algorithm. And in this context, we define the propensity score being the probability that it's in the training set. So the probability that I have spectroscopic data as a function of the photometric magnitude. And what I want to be able to do, well, okay, so first of all, because it's a balancing score, these conditional distributions are the same. The distribution of, as I said on the previous slide, the distribution of x given E is the same. And because we're assuming covariate shift, the distribution of y given x is the same. So now those distributions are the same. And what I want to do with my algorithm is I want to minimize for the target the difference between y, whether or not it's a type 1a, and the prediction of the algorithm. I want to minimize this expected loss, the distance between these two things in some sense. And if I condition on the expected, on the propensity score, this thing is exactly the same for the target where I cannot compute it as it is for the training set where I can compute it, as in the training set I actually have y. So I can train on the, if I condition on the propensity score first, I can train and everything works fine. So how does that work? I have to first estimate the propensity score. So that's relatively easy. I have for every object, I know if it has spectroscopic data or not. That's the, whether or not it's in the training set or the test set. I have all the photometric magnitudes. So I build a model, logistic regression, for example, for that thing. And then what's really nice about these things is I can check. I say that given the estimator propensity score, these distributions have to be the same. Well, I can just make a histogram. That is to say, I take the I take the propensity score, I divide it into the data into groups based on the propensity score, and within groups, I look at the distribution of the magnitudes in each of the filters. And I could do statistical tests to see if they have different means. I can make histograms of them. I can make quantile plots to make sure that everything looks reasonable. If it's not reasonable, because mathematically I know this has to be true, it means that my estimate of the propensity score isn't very good. So I might think about changing my estimate. Instead of using logistic regression, maybe I use a random forest. Or maybe I need to, instead of just having the magnitudes, I have to include the products of magnitudes and other variables as well. But once I've decided that this is reasonable, I then want to condition. And the way we do that is exactly the same. I take the data, I break it into individual groups based on the propensity score. So maybe 5 groups. And within each propensity score group, we train the algorithm separately and do the prediction separately. And because within each group, the fitted propensity score is not going to be exactly the same, but it's much more similar. I get essentially balance among the covariates. So these are pictures. Like this is redshift and brightness, some measure of brightness. I break the data into 5 groups based on that variable. Actually, I'm not going to use just these 5 variables. I'm going to use all the colors. So that in actuality, it's a much more messy, but you can kind of see the distribution nonetheless. And so let's just see how it works. This will be my last slide. So ROC curves. So you can see without an ROC, I can't remember what ROC stands for now, but you can see false. We're trying to classify supernovas as being type 1a or not type 1a. So here I have the false positive rate. So I classify a non-type 1a as a type 1a, false positive. And true positive, I classify a type 1a as a type 1a. That's good. So what I'd like for this curve to do is to go, straight up to 1 and then straight over. Now that would be perfect classification, and that's hard to do. What I get instead are these various curves that are not quite perfect. And one way that people measure the ROC curve, kind of is to compute the area. If the area is 1, that means the curve goes straight up and over. And a higher area means you're getting better classification. So this particular problem, because again, it's based on a simulation, I can use an unbiased training set. So I can just remove the bias. That's the gold standard. It's impossible to actually do, because in the real problem, you don't know. But you get area 96.96 under the ROC curve. If you just ignore the problem, just pretend there's no bias, you get an area of 0.9. So that's kind of the range of possibilities. Not perfect classification, the best classification we could hope for is area 0.965. And the worst we would ever imagine is just ignoring the problem, like the 3.2. There's a bunch of other methods. I'm not going to go into them. Instead of doing this kind of stuff we're describing, they kind of do a reweighting of the distribution of the covariates, the photometric magnitudes in the training of the test set. And that means you have to kind of estimate those distributions or the ratio of those distributions. And there's lots of non-parametric ways to do that. And all of those methods are trying to do that one way or another. The problem with anything like that, though, is when you try to estimate, whenever you have a density in the denominator, you want to go, worry. Think about what, because if that density for parts of the parameter space, or parts of the photometric magnitude space in this case, is going to be close to 0, and this thing is going to become really, really unstable. And even if it's 99% for 99% of your data, it's a completely fine estimator. If for a little fraction of the data, it kind of explodes and gives you wild madness, very highly variable estimate, the overall estimator can be quite bad. And that's essentially what happens with all of these weighting methods. So this is our Stratler method, the top one, and these are various weighting methods down below. So yeah, that's what it says there. Unfortunately, large weights are highly variable, very variable, and cause unreliable target predictions. So I guess maybe I'll stop there. It's right on time. So that's it. Is there any questions or anything anybody wants to talk about before we finish? Anybody online still?
Yeah,
Anita, I heard you.
yeah. I'm always confused about shrinkage, so it's such a weird concept.
Yeah, it is quite weird. I mean, the way I think the easiest thing to remember to think about shrinkage, I'll just go through this little thing one more time. Is again, on this little picture, where if you can convince yourself that by looking at the distribution of those x's in the far right, that the ones that are at the top are more likely to have positive errors because of the distribution of the estimators, then there's some reason to pull it down, your estimate. And that's to me, that's the thing that kind of nails it down for my understanding. Like that's a sensible thing to say.
Yeah, this is a good plot. Yeah, that's a good figure for that. But it's such a weird concept.
Indeed. Okay. Anything else? Oh, go ahead, Ali.
Yeah, so I'm an X-ray astronomer, and I was traditionally trained on the frequentist approach.
Yeah.
How would you suggest moving forward if we want to start using these methods? I know that there are some packages out there like EXA, diffusion X-ray analysis by Johannes Buchner, for example.
Yeah.
Do you have any suggestions on, for maybe there's a student who kind of wants to try from the traditional frequentist approach to get more into the diffusion?
Yeah, well, there are a bunch of packages. That's true. I mean, if you want to try it for the first time, I would try to set up some simple version of your problem where you can convince yourself you're getting some mileage, and then before you kind of build up the whole model. But there are these, it's just, so cosmologists, it turns out, are very, very Bayesian. Right, so they have these packages that are meant to, what do they call it? Multi-nest. So there's the package you described, but there's a bunch of these kind of off-the-shelf packages where you just kind of put in the likelihood and it's going to return posterior draws for you.
But then it's also kind of a shift in thinking about the analysis, right?
Yeah.
And that might be even harder than applying actual packages.
Yeah.
Is there, feel like people are slow in kind of moving from a traditional field? Do you see like in X-ray astronomy, do you see
There's a lot more than there used to be. And you do see, I mean, in parts of astronomy, there's people who are doing quite sophisticated Bayesian analyses these days, right? But I think it still is, and I'm a little biased, right? Because the people I talk to are quite, keen, but that's why they talk to me, right? There's lots of examples now where people can kind of account for the, properly account for uncertainty in ways that are really hard to do from a frequentist point of view. And people can kind of see that when they're, their frequentist analysis are making certain shortcuts that they prefer not to. And if you can show them how you can avoid that, I find that to be quite compelling for people. It used to be, I think, that people were quite, shut the door. They don't, you talk about prior distributions and that was like too much, but I don't think that's really the case anymore.
No, I agree.
Yeah. So it's tricky. It's kind of a case by case basis. I think you just need to kind of identify where you can push things further and try to, convince people, just like science. So, yeah. Very good. Anything else? Yeah, well, maybe I can send an email. So there's a very good general statistics book. Oh, thought you dropped. I thought you spilled your lunch or something. Don't worry about it.
We can add, David, we can add the references to the website with the lectures. Yeah, because there are already 2 of them there, but we can add more.
But maybe I already did. Can you see them? What does it say?
Let me see. I have this. Yeah, so we have this suggested reading, Gelman-Carling, the Bayesian data analysis standard book by Gelman-Carling.
What's the other one?
And the other one is Fred Barnett, Girard, Statistics for Astrophysics, Bayesian methodology.
That one it's a 5-chapter book, and me and David Stenning, my co-author, wrote 3 of the chapters.
Oh, nice.
And those 3 chapters are actually based on these slides. So there'll be citations and references, but it's kind of this in book form. And the references is on the webpage. And then the other one is a general book about all Bayesian things from a very dated, but a really data-driven point. Not thinking about the theory. There's going to be a little theory, but it's driven by how you analyze data, not how you think about the theory. So that's a very good book, I think.
Mm-hmm.
Anything else?
For the slides, I don't think we received the email. It's possible that.
So it's in this, if you have the old email, it's in the same place. The slides are all together. That's probably the easiest thing. I think it sounds like there's some hang up with whoever sends, Anita sends email to the list, and I expect you will eventually get the email. It's just that there's a hang up for whoever's approving it. Yeah.
Yeah. So I don't know if we had the link to the lecture website in the email or not. In the first one, I did send it in the email this morning. The link we can, maybe we can put something in the next events newsletter as well. I'll try.
Yeah, yeah, or if you get that email, I mean, you'll get it too, right? If the email shows up in your inbox later today and it has it all in there, that's fine.
Yeah.
But, you know, whichever you find best. Okay, shall we finish?
Thank you, David.
Okay. Thanks, everybody. It was fun.
Yeah, people go for lunch now, right?
Yeah,
This
it's time for lunch.
yeah.
Okay, talk to you later, Anita. I hope you feel better.
Yeah, thanks.
Yeah.
Have a good trip,
Yeah,
David.
yeah. Okay, bye-bye.
Yeah, bye-bye.